Hello and welcome to Earthquake Tips. My name is Dr. Shailesh Agarwal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor S.K. Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to understand language to our professionals who are in the field designing and constructing structures, especially our architects and engineers. Before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. Today, we are going to look at earthquake tip number 2, which is on how the ground shakes. As you can see in this figure, I told you in earthquake tip 1 that earthquake is a violent shaking of ground due to release of large elastic strain energy through sudden slip at faults. From this fault, this energy travels as seismic waves. Seismic is another terminology for earthquake. So these seismic waves travel in all the directions through earthquake layers, refracting at each interface. When these seismic waves travel through the body of the earth, they are called body waves. And when they travel through the surface, when they come at the surface, they are known as surface waves. Body waves are of two types as shown in this figure: P waves, which is primary waves, and S waves, which is secondary waves. Surface waves consist of love waves and Rayleigh waves. As shown in figure, under P waves, material particles undergo elongation and compression in the direction of energy transmission, whereas under S waves, the material oscillate at right angle to the direction of energy transmission. Now let's look at love and Rayleigh waves. Love waves, which are surface waves, cause surface motion similar to secondary waves, whereas Rayleigh waves make material oscillate in elliptical path. P waves, being body waves, are the fastest, followed by S, love, and Rayleigh waves. S waves primarily do not travel through liquid. However, S waves in association with love waves cause maximum damage to the structure on the surface in both vertical and horizontal directions. Let me also tell you that P and S waves, which are primarily body waves, when they reach the Earth's surface, most of their energy is reflected back to the Earth. Therefore, shaking is more severe. It's around 2 times at the Earth's surface than at substantial depths below the Earth. This is the reason that while designing structures above the ground, we make use of higher level of acceleration than we use for buried underground structures. Now let's move to how do we measure earthquakes. The instrument for measuring earthquake shaking is called seismograph. Uh, the seismograph has three components: the sensor, the recorder, and the timer. This figure shows one of the earliest seismograph recording the earthquake. You can see here a pen attached at the tip of oscillating pendulum. Pendulum is nothing but a mass hung by a string from a support. Uh, this pen marks on a chart paper, which is held on a drum rotating at constant speed. The pendulum mass, along with the string and the magnet and its support together, constitute a sensor. The drum and pen and the chart constitute the recorder, and the motor, which rotates the drum at constant speed, forms the timer. This is one of the earliest seismographs. And as you know, earthquake can come from all the directions. Therefore, seismograph is required for each of the two orthogonal horizontal directions, which we call X and Y, and one for vertical direction, that is Z direction. The earlier seismographs were analog instruments, which are evolved over the time, and today we have digital instruments using modern computer technologies. Having measured the earthquake, let's move how the ground shakes and how do we define strong ground motion. The shaking of ground, as I told you, on the Earth's surface is caused by seismic waves, which arrive at the surface at various instants of time, having different amplitude and carrying different levels of energy. Therefore, the motion at site is random in nature, and its amplitude and direction varies with time. Large earthquakes at a greater distance can produce weak ground motion, and that may not damage your structures. From engineering point of view, strong ground motion, which can often damage structures, are of the interest, and it can happen uh, uh, with earthquake, which comes in the vicinity, or even with large earthquakes with medium to large distance. Let's understand the characteristic of strong ground motion. The motion at the ground can be described in terms of displacement, velocity, or acceleration. The variation of ground acceleration with time recorded at a point on ground during earthquake is called accelerogram or seismograph. Remember, I told you that for measuring the earthquake, the instrument we use is called seismograph or accelerogram, and the recorded motion is known as accelerogram or seismogram. Uh, uh, when we record this earthquake as shown in this figure, the nature of accelerogram may vary and it depends on a lot of factors, uh, such as energy release at the source, type of the fault we have. Remember, I told you dip and strike slip faults. Then it depends upon the geology around. It depends on the soil. It depends upon the travel path of the earthquake waves from Earth's surface to local soil. These exograms are of immense interest to seismologists and geologists, as well as engineers, as they carry distinct information regarding ground shaking, peak amplitude, duration of strong motion, frequency content, and energy content. Let me also define here a very important term called peak ground acceleration. The peak amplitude of this exogram is called peak ground acceleration or PGA. Let's give you an example. A horizontal PGA of 0.6 g is equivalent to 0.6 times the acceleration due to gravity. Means that this PGA can cause a horizontal force on a rigid structure equal to 60% of its weight. Just imagine PGA of 1 g or greater. That will have potential of toppling the structure. During 1994 Northridge earthquake of USA, horizontal PGA values of greater than 1 g were recorded. As I told you earlier, earthquake motion can be divided into two horizontal orthogonal directions, x and y, and a vertical direction. Normally, the maximum amplitude of horizontal motion in two orthogonal directions are about the same. However, the maximum amplitude in the vertical direction is usually less than that in horizontal direction. Most of the design codes take vertical design acceleration as 1/2 to 2/3 of horizontal design acceleration. With this, we come to the end of this earthquake tip number 2. In summary, the ground motion is characterized in terms of accelerogram, which is the variation of ground acceleration with time during earthquake at particular location and can be used for design purposes. You can download this tip from www.bmtpc.org website. The next earthquake tip will be on what are magnitude and intensity for earthquakes. Thank you.